Hello everyone and welcome to this video presentation. Today I will be explaining our project titled Perceptron for Vertical versus Horizontal Edge Classification. This project is part of our digital image processing coursework, where we combine concepts from image processing and machine learning to classify edges within an image. Edges play a vital role in understanding shapes, detecting objects, and identifying boundaries in any visual scene. Classifying edges helps in several applications like image segmentation, feature extraction, and object detection. In this work, we build a simple yet powerful model, the Perceptron, and train it to differentiate between vertical and horizontal edges based on Sobel features. The problem we aim to solve is, given an input image, how can we automatically classify each pixel as belonging to either a vertical or a horizontal edge? To do this, we compute the Sobel edge features. Sobel filters extract the intensity variations in an image. Detects vertical edges, detects horizontal edges. We take the absolute values of these gradients. These two values become our feature pair for each pixel. Based on which value is larger, we generate labels for training. Finally, we train a perceptron to learn a straight-line decision boundary to distinguish the two classes. Let's talk briefly about the mathematics behind the perceptron. A perceptron is essentially a linear classifier. It takes weighted inputs and passes them through a sign activation function to produce an output of either +1 or -1, which in our case represents vertical or horizontal edges and are the weights, is the bias, and are our Sobel features. During training, the model adjusts its weights based on errors. This iterative process gradually rotates and shifts the decision boundary so that most training samples are correctly classified. Even though it's one of the simplest machine learning algorithms, it performs surprisingly well when classes are linearly separable, which is true in our problem. To prepare our data, we begin by applying Sobel edge detection. Sobel operators are 3x3 convolution masks that find the rate of change in pixel intensities. These are the masks: GX mask, GI mask. Applying these masks gives us two gradient images. Where the vertical gradient is strong, we get prominent vertical edges. Where the horizontal gradient is strong, we get horizontal edges. These two gradients are not only edge detectors, but also serve as numerical features for our machine learning model. This is why they are perfect for feeding into a perceptron. After computing GX and GY, the next step is dataset creation. For every pixel in the grayscale image, we compute. Now, how do we decide the labels? We use a simple rule. If, then it represents a vertical edge. Otherwise, it represents a horizontal edge. This labeling gives us thousands of samples from just one image. We then store these values in arrays and use them as input for perceptron training. By visualizing these points on a scatter plot, we notice that vertical edges tend to cluster on one side and horizontal edges on the other. This visual separability confirms that a perceptron can learn a good separating line. Once the dataset is ready, we train the perceptron. The process is straightforward. 1. Initialize weights and bias to 0, 2. Loop through the entire dataset 3. Predict output for each pixel 4. If prediction is wrong, update weights 5. Repeat for multiple epochs. After several iterations, the perceptron converges. What this means is that the decision boundary stabilizes and the model consistently separates vertical and horizontal edges with high accuracy. This step is essential because edge classification often requires precisely identifying subtle differences in intensity variations. In our implementation, we used Python along with OpenCV and NumPy. OpenCV helps compute Sobel filters, while NumPy handles vector operations for perceptron training. The main parts of the code include converting image to grayscale computing Sobel gradients, preparing input feature matrix, training the perceptron using loops, plotting scatter plots and decision boundary, classifying every pixel and generating the final output image. The code is concise and demonstrates how easily machine learning can be integrated into classical image processing tasks. Here, you can see our final edge classification output. The image has been processed pixel by pixel, and each edge has been categorized as either horizontal or vertical. The model performs very well and produces a clean separation between the two edge types. To conclude, this project demonstrates how traditional image processing and simple machine learning techniques can be combined to achieve efficient edge classification. Thank you for watching.